So I might stop in between. ಯಾರೇ ಇದನ್ನು ಬರ್ತೀವಿ ಹೌದಾ? Okay, thank you. I'm just going to ask you to help me to put this. Oh, actually, yeah, we should record this because the Zoom participants also want to attend the tutorial. Oh, yeah, my nose. Oh, Fourier. So let's start then. It's anyway time. So let's begin. So remember that. So in the first half, what did we discuss? We discussed pseudo-Riemannian geometry, right? And the basic element, the basic field in pseudo-Riemannian geometry is the metric, right? So it's some rank 0 to tensor, some g min u of x, right? And what we discussed about g min u of x is that g min u of x under a coordinate transformation under. So I'm just reminding you of some basic facts. If you have some questions, please ask. Under some coordinate transformation x going to x prime of x, g min u of x transforms like this. Pseudo-Riemannian, okay, Riemannian geometry, you understand, right? So Riemannian geometry is anything that a geometry with a metric, right? Pseudo basically means that the metric has a negative eigenvalue. That's all it means. Okay, it's just a name. You don't have to worry about it. Okay. So yeah, the metric transforms like this, mu alpha beta, g alpha beta, right? And this is the transformation law for a 0 to tensor. So the metric was a 0 to tensor, and that was one of the basic fields that is the basic field in pseudo-Riemannian geometry. So okay, so why does the metric transform this way? Remember that the metric is what allows you to define distances on a manifold. So you're in some manifold. I'm in R3 right now, or R4 if you include time, and I want a distance in this manifold. Okay, then the distance is given by some invariant line element, right? And the line element is what defines this metric. I mean, people call this also the metric sometimes interchangeably. So the line element this way at every point in space time defines the metric, right? So now this has to be invariant. How much you have changed in one coordinate system is the same amount you have changed in another coordinate system. I can't say you've moved different amounts if you've moved some amount. So then you know how this transforms. So this has to transform in the opposite way. That's it, right? So this is one way of looking at tensors and vectors in general, is to write down an invariant element. That doesn't change. But if you know how these changes, right? Under coordinate transformation, you know how these change. So you should know how this changes. That's it. Okay. So that's the basic field of pseudo-Riemannian geometry, and or in more generally Riemannian geometry. Now, one of the first exercises that I found, I mean, I might miss a few exercises, so you should remind me if you want me to do something more. But one of the first exercises was to show that if the metric transforms as a 0 to tensor, you have to show that the inverse metric, also called the cometric. So let me define the inverse metric, or sometimes called cometric, g min u of x is defined by this equation. Note that this is a Kronecker delta that doesn't have a dependence on X. At every point in space-time, you define an inverse metric, right? You regard the metric as some matrix, and at every point in space-time, you find the inverse of that matrix. Okay. So now, I don't know if any of you have done this problem. If G rho nu transforms as a 0 to tensor, what do you think this transforms as, just by notation? As a 2, 0 tensor. But how do you show that? Did anybody work this out? No? Okay, so you're saying let's take this equation and put the arrow through it, basically. Yeah, so let's take this equation. So whenever you want to so this defines for you the cometric, right, by this equation. So if you know the transformation of this, and you also know the transformation of this doesn't change, right? It's just Kronecker delta, it's just some invariant matrix. So then you can find the transformation of this, right? So let's do that. So I will do many things explicitly. It might be boring. So let's transform this equation. G rho nu of X equal to delta mu nu transforms into G prime mu nu of X prime, which we don't know, G prime rho nu of X prime, which we do know, and this side has to remain delta mu, right? Because delta mu nu is invariant under coordinate transformations. This statement is clear to you guys? You know how to show that? Because delta mu nu, if you do the transformation, again will just give you a delta mu nu. The partial derivatives will just contract. Okay. So let's do this. So G prime mu rho. So let me just probably do this here. G prime mu rho of X prime. And then that bit I know from the invariance of the line event, I know how the metric transforms. So let me write that down. Alpha over del X prime rho del X beta. Also, while I'm writing these expressions, you should check, because I'm this close to the board, I might make mistakes. Equal to yeah. Okay. Now, what is the only way to solve this equation? I claim that the only way to solve this equation is the following. If let me use some other symbols, gamma delta G gamma delta of X. If this is true, then the above equation is satisfied. We'll check this. Right. So let's put this in there. Let's see what we get. I hope I'm not repeating indices. If I repeat too many times, you should let me know. I'm trying to use as many indices as possible. Different indices. Superscript in the middle term. This one? Yeah. Rho and delta. Huh? Delta. Delta. And so that's this piece times G gamma delta times this whole piece. Right? So what's the simplification here? Did I make it? No, yeah. What's the simplification here? Okay, not cancel, but yeah, these partial derivatives, the whole thing is just delta alpha beta. So let me call that delta alpha beta. So this bit hits that bit and gives delta alpha beta. Huh? Sorry, delta alpha delta. Yeah. Okay. So then that becomes del X prime mu over del X gamma times del X beta over del X prime nu. G gamma delta G alpha beta, but delta is alpha. So G alpha gamma alpha G alpha delta alpha beta but that is defined in the original X coordinate system. That's just delta gamma beta, right? So once you put delta gamma beta, this becomes beta. Again, these partial derivatives contract, and then you get mu nu. So this is delta mu. Did you understand that? I skipped like 3 steps and written down the answer there, but you get it? Okay, great. Okay, so this is the basic field and its inverse. So we'll use both of these extensively in formulae, which we have seen, right? We use both the cometric and the metric in many formulae that we write down. If you're writing down the Riemann tensor or if you're writing down the Christoffel connection, in all of these, you have these both coming up. But what more can we construct from the metric? So this is matrix multiplication. It's not like matrix multiplication. It is matrix multiplication. Okay, because everything is in coordinates, so it is matrix multiplication. Now, if you want to say that you want to think of I didn't quite understand the latter part of your question. Could you repeat it? There is no transformation here. This okay. So let's say you have a matrix A, okay, and you want to find its inverse. The inverse is defined by this equation. There is no transformation going on here. Sure, you want to transform A, since it's a matrix, let's say you want to transform it by a U, you would have to transform it like this. More generally, U inverse, AU. There's nothing like that happening over here. This is just the definition of the inverse metric or the cometric. Okay. There is no vector here. Okay, so you want to. Okay, let's say A is some tensor and some vector, and then what do you want to do? You're asking me, okay. You're asking me what is this object? Say in general, yeah. Okay, this is just this. Not index size. Okay, so this is the non-trivial statement that the metric allows you to take a vector to a covector. Okay. For those of you, I think most of you are familiar with differential forms. If you're not, don't worry. I'll just make a quick comment. If you're doing differential forms, okay, if you know some differential forms, you know that one forms are defined separately from vectors, right? What the metric does for you is to relate the vector and the one form, as you can see here, right? Because this is a one form. You should think of this as a one form. It's a V mu dx mu. That's a one form V. But this is a vector. It's a V sigma or V alpha del alpha, right? Vectors are directional derivatives. So you're taking a vector to a one form, and the metric allows you to do that. But that's a quick comment that won't bother us here. Okay, good. Okay, so next, yeah. So then. Okay. So then we can come to what else can be formed from the, what are the other tensors you can form from the metric, right? Because remember that the basic principle that we have been using all throughout is the principle of general covariance. You should never write down anything where the tensor indices are wrong. You should not write down equations where the tensor indices are wrong, right? They should match on either side, okay? So you should write only tensorial equations down. So then you ask, G mu, of course, is a tensor because it transforms as a tensor. What other tensors can you form from G mu by taking its derivatives or any algebraic multiplication or division or what kind of things? Okay. So then immediately one obvious answer, tensors from the metric. Remember that eventually you want to write down an action for gravity, right? Which is what we did last time. Remember? And we got G mu equal to some constant times T mu. Right? In doing that, you only write down things that are covariant, right? That are tensorial. So you want to find tensorial quantities from the metric. So then after giving you guys this exercise, Ashoke gave you this exercise of showing that G mu 1 mu 1, G mu 2 mu 2, which now notice is again a tensor. Okay, this was one of the exercises to show. Do you want me to show you this? Because this is very obvious, right? If you know that G mu transforms this way, there are 2 G menus. You just have to take 2 of this and stack it together, right? So this is like very simple. Let me just do this for you. So this transforms to the first one transforms with a, let's say, del x alpha 1, del x prime mu 1, del x beta 1, del x prime mu 1, and then you get a del x alpha 2, del x prime mu 2, del x beta 2, del x prime mu 2 times g alpha 1 beta 1 g alpha 2 beta 2, right? As very obvious. So you can just think of this as a 0-4 tensor, mu1, mu1, mu2, mu2. Okay. So that's a very simple way of forming tensors from the metric. You can just multiply them together. Okay. And in general, and in more general, you can put many things together. You can put things like this together, or you can like keep doing. You can multiply and do it however you want. When I say divide, I basically mean using the cometric, right? So you can use. So we have shown that both the cometric and the metric are tensors, but they're tensors of different form, 0, 2, and 2, 0. And from them, you can find any different tensors. So for example, if I remove these dots, what is the rank of this tensor? 2, 4. So that's a 2, 4 tensor. Okay. So then it seems like we've exhausted possibilities with algebraic multiplication or algebraic operations on the metric. Okay, you have given some matrix, which is the metric, and you can do algebraic operations, which are just multiplication. So we are done with that. What else can we do? Derivatives, exactly. So then you can ask, so let's say this is algebraic. So this was the second exercise showing that this is a 0-4. And then you can do derivatives. Okay. Let's first stick to first derivatives. Okay. So let's say A, first derivatives. So can you form a tensor with first derivatives? No, right? This is a theorem we proved in class. I'll not prove it again. But basically the point is that the first derivatives of the metric, you can always just set to 0, right? So you just cannot form a tensor from it. This was something that was proven explicitly, precisely in the class. So no tensors here. But there is a very important quantity lurking here at first derivative order, which is the Christoffel symbol. So this is not a tensor. I make it extremely clear that it is not a tensor. I'm discussing this under the tensors formed section, but it's not a tensor. Okay. So but I want to discuss it because it's a very important quantity. And that's another exercise. Let me find the report. I will explain that. Okay, so let's come to the Christoffel connection. Of the Christoffel symbol. Just so that you can look up these things in different books and not get confused by the names, let me just note that this is sometimes also called the Levi-Civita connection. The name connection makes sense because when you do parallel transport or when you do a covariant derivative, this is the quantity that you need to use. Okay, hence the connection. And I mean, there are more deeper meanings to the word connection, of course. So the Christoffel symbol, remember, was just some gamma mu rho. Let me use alpha beta. And this is not a tensor. Not a 1-2 tensor. Okay. So you never raise and lower indices on this one. Okay. And if you ever do, you should be very, very careful. Okay. So you should be very careful with this quantity and raising and lowering indices on this one. This is not a tensor. And secondly, in writing down things, so when you write down a tensor, you have to be careful about where the indices are. You can't just write things like this, right? Because here it seems like you can't lower or raise anything. You always write indices in order. right? But here you don't have to be careful with that. The Christoffel connection you can just write, because here you will never, almost never raise and lower. Okay, so this is not a tensor, but this is useful. Why? Because we want, if remember that in parallel transport or in defining a covariant derivative, you want to define a derivative that is tensorial, right? This becomes useful covariant, by which I mean tensorial, why though? Why is that? Why is it that you needed such a quantity to define a covariant derivative? Okay, so let's say you took a vector. Let's say you took v mu, and I just did del nu. This didn't work, right? Why didn't this work? It gave an extra term, right? It gave an extra term, and so this doesn't transform like a tensor. So then now you say I want to add something to this such that it becomes a tensor. So let's say I add a quantity, I add some quantity times some v rho. The quantity has to depend just on the vector. And what kind of quantity can I put here? Just to make sure all the indices are correct. Always remember that you write down equations, just make sure that the indices are correct. First thing you do. Okay. So if I want the indices to be correct, I have to put a nu there. Mu upper, rho low. Okay. That's what we define. Okay, this is I'm used to the covariant derivative being a nabla, but Ashok has been using D, so I'll use D. But if at some point, just by habit, I use nabla, correct me. So D, no, D. Okay, that we defined was the covariant derivative. And since this didn't transform like a tensor, this did transform like a tensor. This gave an extra piece, which should be gotten rid of, right? So whatever extra piece is here should not transform like a tensor. Does that argument make sense? Because if this transform like a tensor and this transform like a tensor, this also has to transform like a tensor, right? Okay, so tensor, not a tensor. Hence, not a tensor. So now we have concluded that gamma mu nu rho does not transform like just del del x, del del x, del del x, 3 del del x, and then some gamma. It does not transform like that. It transforms with an extra piece. And that extra piece is exactly what cancels the extra piece from here, right? So let's fix what gamma mu transforms as. And that will be the third exercise. And there are multiple ways to do this, okay? One way is to just brute force do this by starting from the Levi-Civita connection. Let me use alpha beta. Okay. What? Right? So that was the Levi-Civita connection. This definition Ashok just gave you, right? And then he asked you to check from here that the Christoffel connection has some transformation law. Okay. Now that's quite a tedious exercise which we can do. If you really want to do it next class, maybe we can sit and do it. But let me show you another way to get how gamma mu transforms, how the gamma transforms, how the Christoffel gamma transforms. We can just start from here, right? You can say this should transforms as a 1-1 tensor. We know how this transforms. And then we can find how this transforms. So let's do that. D mu has to means I'll run out of symbols. So. You agree with that? Okay. But then which itself transforms as plus some gamma prime, which we don't know, which is what we're trying to fix. Then we know how to transform. Is this okay with all of you? I've done two things here. One is to just say that in this equation, this side has to transform like a 1-1 tensor. So this side has to transform like this. But we already know how this transforms, and this, I'll just say it just transforms as a gamma prime, which we have to fix, and we know how this transforms. So I just written that down here. So now this has to be equal to that. So let's just put that down, and I will differentiate. Let me know if I make a mistake. The system plus which should be equal to the 1-1 tensor transformation. Right? Now, do you see anything happening? Anything cancels, maybe? Okay, do it. Which term? Cancels, right? And that's easy to see. Is that easy to see? Never, always think of indices that are repeated. You should just forget them somehow, right? So this is repeated, and that comes with a new. Note that V rho, that is also repeated, comes with a new. Again, sigma with a mu, beta with a mu. I can explicitly relabel them just to make it very clear. I can call rho alpha, and I can call sigma beta. No, this is just one term, right? If I have a term like P rho W rho plus A rho W rho, I can just change indices here, right? Yeah, come. Which term? Here, yes. Okay, what did I do? Should not have done this. Which one is sigma and which one is rho? Okay, alpha was rho, right? Alpha was rho. Okay, let me call this epsilon. Epsilon, what was that? Alpha, beta. I think this is correct. Why not? I think this is correct. Fine. Did it confuse anybody? I can do this again if it confused somebody. Okay, so that means the first term cancels. This cancels against that. And we're very close to the final thing. So we get, let me start from this side. Gamma prime mu nu alpha del x prime alpha over del x beta v beta equal to del x alpha over del x prime mu over del x beta gamma beta alpha epsilon b epsilon minus okay. Now v, remember, is arbitrary. I want to get rid of it from both sides. What do I have to do for that? Relabel indices, right? Relabel indices and then cancel. So let me call this epsilon. Epsilon. That is already an epsilon, so that's fine. Let me call this beta also an epsilon. Epsilon. So then the v alpha just v epsilon just drops out because that's an arbitrary 1, 0 vector. So that just drops out. And next, I want just gamma prime on one side. I don't want this bit. I want to pull it to the other side. What do I do? Multiply with the inverse metric. Right? I mean, inverse of this matrix. So let me multiply by del x epsilon over del x prime beta. Or let me say rho. Am I using a rho there? No. Yeah. This is okay? I'm just multiplying by the inverse of this matrix. So now this del x epsilon will just contract, and then that will give you del x prime alpha, del x prime rho. That's just delta alpha rho. Does this make sense? Yeah. And then the delta alpha rho will just set this alpha to rho. So you get gamma prime mu rho. You should stop me if anything confuses you. Equal to, let me write this as del x prime mu over del x beta, del x alpha over del x prime mu, del x epsilon over del x prime rho, gamma beta alpha epsilon. Now this would have been the tensor transformation law if gamma were a tensor, but it's not. So you get an extra piece. Yeah. And that's how the Christoffel connection transforms. Actually, the answer that Ashok gave you asks you to transform this a bit further. Do you have your notes? I mean, you can check whether the second term matches. Does it? Okay. It's not matching because here in that answer, he has a double derivative of x with respect to x prime coordinates and not the other way around, right? So you basically, okay, this I don't know if I should do, but let me tell you what is happening here. Let me just erase this. Hmm? This one? This beta? Yeah. That it's a wait. Did I write this correctly? Yeah. Row. This row. Yeah. Sorry. Yeah. Okay. What Ashoke has written is basically trying to use this identity. Uh, This identity makes sense to you guys? I'm doing nothing non-trivial. I'm just saying you take delta alpha beta, you do some del delta, that bit is 0. But I have a way to write delta alpha beta down, just like that. Okay. And so that is 0. Actually, I don't know which one to use, whether del x prime or del x, but let's just try. Let's try if I can get there. If I don't, I'll just leave it to you guys. So here, what will I get? I will get gamma. What is this bit? This bit is just del squared x prime alpha over del x. Let's say epsilon. Okay, I think this should be it. Is that it? I think this is what you should use. Should I relabel indices for you guys? Let me see. Let me call alpha mu. Firstly, you should stop me if I'm going too fast because these relabeling of indices can really confuse people. Alpha and epsilon. Let me call gamma alpha. So alpha and epsilon, and then you want a new row. So let's call delta as new. Delta is row. And then this is a new. They should agree with the formula in class, right? The minus sign goes away because of this minus sign. And then these three, the product of these three matrices becomes the product of just two matrices. So that's one of the exercises to find how the gamma transforms. And another one exercise that I found in here, but that's probably already clear to you guys, is to show that. Okay, let me come to that. Is this fine? Everybody? Okay. So we're done with first derivatives. First derivative, we said that there's no tensor, but there is a very important quantity with which you can define the parallel transport or the covariant derivative, which is the crystal connection. So first derivatives are done. Let's go to second derivatives. So one lesson all this teaches you is that sometimes you have to be careful with the notation. Just because I write del mu b rho does not mean this is a tensor. It does have two indices below. It does have two tensor indices, but that doesn't mean it's a 1-1 tensor or a 0-2 tensor, right? So you should be very careful with that. So let's come to second derivatives. B. So one of the exercises here was to check that this is not a tensor. It's probably already very obvious to you guys. But let's just check it. How does this transform? So this is what? This is just del x mu, del x nu, g alpha beta. So this under x going to x prime of x transforms as what? It transforms as del x over del x prime mu. What do I call it? Rho del over del x rho of del x sigma del sigma over del x. It's not enough space. So let me transform the first derivative first. First derivative transforms as a del x over del x prime mu rho del over del x rho. And then the second derivative transforms with a del x sigma over del x prime nu del over del x sigma. And then the metric also transforms, which gives you a del x gamma, del x delta over del x prime beta, del x prime alpha, gamma. Naively, if you didn't know this fact that this is not a tensor, you might have thought that this is a 0-4 tensor. But if that had to be a 0-4 tensor, you should just get like 4 Jacobi matrices here, Jacobian matrices here, and you should get G. Does that happen? Clearly not. Right? We can do a few more steps and write everything down, but that's just a big mess on the board side. I'll just stop here. Okay. So that's not a tensor. But then how do we form a tensor? Right? Because eventually we'll assume that in writing down the Einstein action or the Einstein-Hilbert action, we'll say we'll only keep to second derivatives and we want a tensor at second derivatives. We want a scalar quantity that is formed out of all up till second derivatives, all the tensors you take, put everything together, find scalars and put all the scalars in the action. That's our strategy, right? At the end, with last class, that's what we did. So I want tensors at second derivatives. You can also keep going, tensors at third derivatives, fourth derivatives, fifth derivatives, and so on. That will not be Einstein GR, but there'll be corrections to GR. In GR, you only work till second order, second derivative, not order. Okay. So how do you form a tensor? That's a very interesting question, actually. Venture a guess. How? Sure. How? How is the point? So what is one quantity that you did see, which was at second order in derivatives, which was also a tensor? Riemann, right? And what did Riemann look like? So example here. So this was not a tensor. But a proper example of a second derivative quantity was the Riemann tensor. And then you can contract the Riemann tensor to form the Ricci, which is also second derivative, it's just contracted, so also a tensor. And from the Ricci, you can again contract to get the Ricci scalar. Then you can actually keep going on. You can contract 2 Riemanns and get like the Kretschmann scalar, etc., etc. You can do many things. But at second derivatives, basic quantities is just the Riemann tensor. We also discussed the uniqueness sort of in the last class, right? So once you get the Riemann tensor, you can get all of this. So this is the main thing that you have to remember. Okay. But we wrote down the formula for the Riemann tensor in the class in terms of some del gamma minus del gamma plus gamma gamma minus gamma gamma, all the indices. But how do you think you can like fix this gammas? How do you, okay. So for example, in this case, where is this case? In this case, I wasn't going to find a tensor. I was just going to find a quantity such that I can define a tensorial derivative, right? So I started with the fact that I want a tensorial derivative. If I had a vector field, I want to write down a tensorial derivative for the vector field, say the gauge field, say the Maxwell field, A mu. I want to write down a tensorial derivative. If I had to do that, I have to introduce something like this, something that transforms like this. So what is what is something similar for the Riemann tensor? Derivatives of? Yes, derivative of Christopher symbol, but how do you find it? Okay, I mean, I'm asking for too much. Let me just tell you. What should I erase? What should I erase? Should I erase the top ones? Because top ones will cover this. That's okay, right? Derivatives of the covariant derivative. Let's see. Exactly, that's the answer. So remember that the basic intuition, I mean, remember at the end of the day, we're doing all of this geometry to describe spacetime, right? Curved spacetime. And the running intuition behind our minds for the Riemann tensor is that it gives you the curvature. For example, if you compute it for a sphere, for S2, you'll get it as 1 by a squared, right? Where a is the radius of the sphere. So it tells you that the sphere is actually curved, right? So with that intuition that the Riemann tensor is actually telling you something about the curvature, you might ask, let's take a vector, say 0, okay? And let me do a covariant derivative along one direction. Oh, sorry. Say the mu direction. Okay. So what does this mean? This means that on your manifold, say this is some manifold M, and you've put some coordinates in some, so you're sitting in some patch here, and you've put some coordinates. Say this is the x mu line. So say this is x0 and x1, and you have put many of these coordinates. So mu, I'm just taking one of these coordinates. Mu can range from 0 to d minus 1 if you're in a d-dimensional manifold. And I'm taking one of these directions, doing a covariant derivative along that direction, right? Which is a derivative that's tensorial along that direction. And that is the only kind of derivative you should take, only tensorial derivatives. Okay. So I change it like this, let's say. And then I say, I'll just take the muth direction and mu in the muth direction. I'll take another derivative in the muth direction. So that's what you mean. Okay. And then I say, let's do this opposite. Okay. Let's just say I first move along the nuth direction, then move along the nuth direction, same vector, and then ask the question, is this the same? Right? If it is not the same, it's telling you that something happened in between, that there's some curvature in between. And that's our intuitive notion of Riemann tensor, right? So what I want to do is to formalize this into a Riemann tensor. Yes, exactly. So let me do that. Notation will become a bit messy. So this is how one defines the Riemann tensor. And also here, notice that since I'm doing these new mu, I'm doing, say you do first direction, say 0th direction, first direction, and then do first direction, 0th direction. They might not be the same. But if you do same direction once and again, that should be the same. So obviously already you start seeing that the Riemann tensor should have symmetry properties. It's not at all surprising that at the end of the day, the Riemann tensor is not some crazy big object, but actually a smaller object, some n into n plus 1 over 12 or something. I don't remember the number, but something like that. So these symmetry properties are not very surprising, this way of thinking about it. Okay, so let me define the Riemann tensor this way. So you take a commutator of such things, which is basically just the difference between these two. That's where the commutator comes from. It's not surprising. V rho. Okay, now this is where I'll get into some mess because I usually define it with, I mean, since the symmetry properties are true, I usually define it in another way. So I just don't want to confuse you guys. So let me just check this expression once. Yeah, that's fine. that. So this defines really the Riemann tensor. Okay, and that the Riemann tensor is such a basic quantity that you should never forget what it is. Okay, first of all, you have to have this intuitive notion that it specifies curvature, and the trace of it gives you the Ricci, and then you do again a trace, gives you the Ricci scalar, and that scalar is what goes into the action. Okay, so now don't you think we can find R? Because I just have to evaluate this explicitly, cancel B rho on both sides, and just find R. Okay, so let's just do that explicitly since we have time. Yeah, this is some calculation that yeah, just has to be done. So this, remember, is just that's plus gamma rho nu alpha d alpha. Now, how do I take another covariant derivative? This Ashoke discussed. So this is a 1,1 tensor. So what is the covariant derivative of that 1,1 tensor? Okay, so let me say I have A alpha beta, say 1,1 tensor. What is d rho of this? D mu of this? Partial derivative plus gamma beta up. Okay. Does everybody else get this? Get what I'm doing? Okay. I'm just trying to write down a covariant derivative of a quantity with a lower index and an upper index. Okay. Let me just write it down. Let me do this. Let me do this index first. This makes sense to you guys? Sigma. Alpha, mu, and beta are the free indices, and alpha, mu, and beta are free indices everywhere. Does it make sense? Always remember that, I mean, this is something that should become muscle memory as you do it more and more. Once you do a few exercises, it'll become muscle memory. To write down a covariant derivative of a vector, all you need to do is just take the partial derivative and then put the Christoffel connection with the plus sign, right? That defines the Christoffel connection. But which is why there is a definition symbol here. But here, when you do for higher tensors, if you just have like, if beta was just down, then you just have another plus gamma, okay, where you take the second index and contract. Okay, but since here beta is up, you put a negative sign. Sorry, alpha is down, you put a negative sign. For vectors, for upper index objects, you always get a plus gamma. For lower index objects, you should get a minus gamma. Just a minute. Did Ashok explain this minus sign? That this is the covariant derivative for higher objects? I mean, I wasn't in this class, so I'm okay. Okay, let me say a few words about this. I didn't see that exercise. I didn't know that was an exercise. Yes, go ahead.
So it already had a plus. So the origin of negative sign not explained.
Okay, so I remember that I defined the Christoffel symbol by using the vector. Okay, and this is how the Christoffel symbol is conventionally defined. It's defined as a plus gamma for the vector. Okay, so now the point that there is a minus sign for the lower index object, I guess, wasn't explained. So let me just explain that before going here. So one thing you have to note is that the covariant derivative on a scalar is just normal derivative, right? Because this transforms like a tensor. That's obvious. This just gives you a Jacobian matrix. So on a scalar, you don't have to do extra business. It's just the normal derivative. So then you can say that if you have d mu v rho, which is a scalar, just a form and a vector, that is just del mu V rho, V rho. Sure. No, but they have to be, oh, yeah, okay. You're saying VW? Yeah, sure. Okay. Sure, yeah, fine. Why not? We can do VW. VW is also a scalar. This is just a dot product. That's a scalar. Right. So that's true. But then the covariant derivative obeys the Leibniz rule. That's one of the constraints you put on the covariant derivative. You want a derivative that obeys the Leibniz rule. So then you get V rho del nu W rho plus D nu V rho. And this bit has to be equal to V rho del nu W rho plus del nu V rho W. Now you know the definition of this object in terms of the covariant, I mean in terms of the gamma, Christoffel gamma. Put this in here and then just find this. You get the minus sign. Okay, that's where the minus sign comes from. So now I have shown you that the minus sign comes for any lower index object. So now if you want to generalize this for an arbitrary number of upper and lower indices, you can just contract those two things and then find that for all lower indices you get a minus. Okay, does this make sense? Yes, no, maybe. This argument? Okay, let me just do it. So here I'm saying that we want to know this, right? We don't know how the covariant derivative acts on a lower index object, and that's what I want to find out. But I know what the covariant derivative acts on a upper index object is. That's just this. Then it's just that. Yeah. So then you can take the upper index object, substitute it here. This side is just partial derivatives anyway. There's nothing to substitute. Substitute this here, take it to the other side, cancel, and you'll get the minus sign. It's obvious, right? Because you're putting a plus gamma on this side and then take it to the other side, you'll get a minus sign. You want me to do this? Let me just do this. Some of you seem puzzled. Actually, I'm doing this because sometimes you make an argument, it seems very obvious, and then you try to write down all the indices and you realize something's wrong. So maybe that will happen here. Let's see. So V rho del nu W rho plus D nu V rho we know. D nu V rho is just this. So that's just del nu V rho gamma V rho. W rho, yeah, W indeed. Make sense? Don't get confused in what I'm trying to do. I'm just trying to define the covariant derivative for lower index objects. Okay. So then what cancels? This term cancels, right? So that goes away. That goes away as it should, because I don't want derivatives of V in a formula for derivative of W. V and W are completely independent. You get V rho. Let me call this nu rho V rho alpha. I just interchanged alpha and rho. Okay. You should get used to this, which is why I'm not explaining it too much while I'm doing this. So then let's cancel all the V rho's on every side. V is just completely arbitrary. Cancel it off. So you get sorry. Yeah. Okay. So this is how you define the Christoffel gamma with a plus index for the vector. So now for the one form, for the W rho, one form of the covariant, yeah, covariant vector, covariant tensor, 1, 0, 1 covariant tensor, you get this. Now you can just generalize this to arbitrary things, right? You can just put like many upper index, many lower index, multiply, form a scalar, differentiate, equal to 0, get this. So basically the idea is whenever you have an upper index, you get a plus gamma. Whenever you have a lower index, you get minus gamma. Okay, remember that. Where is that? Okay, so that's the definition derivation of that. Let me come back to the Riemann tensor. Okay, so in the Riemann tensor, I needed del mu of del nu 0. So this is coming back to the Riemann tensor. So what is this? First, the partial derivative of this quantity, yeah, plus minus a gamma for the nu, sorry, the 0. Yes, remember that this is a 1-1 tensor. That's what I'm doing from this formula, and then you get plus gamma mu t mu b alpha, say alpha. Make sense? Okay. Now we have to do a lot of work, put all of the covariant derivatives explicitly. But this work is good because it'll show you where the Riemann tensor comes from. Okay. And this explains the symmetries of the Riemann tensor. And I'll also show you the symmetries of the Riemann tensor. That's the exercise I wanted to get to, but I didn't just want to write the Riemann. Actually, I don't remember, so I can't just write the Riemann. So del nu 0 plus gamma nu gamma. First term minus gamma alpha nu del alpha is gamma alpha beta plus and please correct me when I'm repeating indices too many times. I don't think so. Is that okay? Someone peeping from the door. Remember that our work will be done once you evaluate this. Okay, subtracting the other one is just taking mu and making it mu and just switching. So let me do the work. So let me assemble it such that I can just cancel things when I anti-symmetrize. Yes, you'll see we can. There is no limit on 0. 0 is just some arbitrary vector. Eliminate it. Okay, another thing that reminds me, another thing that I should have said here is that this side is a tensor, right? D mu of rho is a tensor, D mu of another D mu of rho is also a tensor, right? Because covariant derivatives are defined to be tensorial. So this side is a tensor. That's a tensor. So this has to be a tensor. Hence it's a Riemann tensor. Okay. So I don't have to, at the end of this derivation, I don't need to show that the Riemann is a tensor. Because remember, gamma was not a tensor, but this del gamma minus del gamma plus gamma gamma minus gamma gamma is a tensor, which I won't show, right? Because I will derive that expression, starting from the fact that it is a tensor. Okay, so it's a Riemann tensor. So you get a del mu v rho, which will cancel eventually when we anti-symmetrize. Yeah, now is when the work starts because I have to start differentiating. Plus del mu gamma rho mu alpha plus del mu. Yeah, as he says, if the v's remain, it basically means I've made a mistake. You would have to correct it. Gamma rho mu alpha. Sorry, what? Okay, first term. Are you guys checking alongside or are you just writing? Minus gamma alpha mu del alpha v rho. I will freely switch mu nu's because it's symmetric. Christoffel is symmetric. Minus, you already start seeing the gamma gamma. So alpha beta v beta. And you see where the two gamma gammas come from, right? One should come with a plus, one should come with a minus because you're taking these two different covariant derivatives. Plus gamma rho mu alpha del mu v alpha plus gamma rho mu alpha gamma alpha mu beta. Now hopefully all the derivatives of v should cancel. Or I've made a mistake. So okay, so let's anti-symmetrize this. So under anti-symmetrization, if I take a covariant derivative and anti-symmetrize v rho, this term cancels. So let me call this blue arrow and anti-symmetry arrow. So under anti-symmetry, this term cancels. What else cancels? Fourth term. This term? Yeah, again. Yeah. Let me come there. So this cancels because mu. Then I wrote this wrong. Okay, yeah, that will also cancel. So this cancels, this cancels. What else cancels? These two will cancel. Right? If you write a mu nu exchange of this, let me write a mu nu exchange of this. You'll get gamma rho mu alpha del mu v alpha. Okay? And I'll write a mu nu exchange of this, which is a gamma rho mu alpha del mu v alpha. And then I have to subtract these mu exchanges, right? So this cancels with that term. So this cancels with that. Following? And this cancels with that. So happily all the del nu's go away, del v's go away, right? If del v's were there, what you said would have been a problem. They do go away. There is a derivative of gamma. Okay, so help me write this down. Del mu gamma rho mu alpha v alpha. Let me pull the v alpha out. And then under anti-symmetrization, this will give you del mu gamma rho mu alpha. And then times the v alpha. What else is there? Gamma gamma. Plus gamma rho mu alpha gamma mu beta minus a gamma rho mu alpha gamma alpha mu beta times a v beta. I'd have to do a lot of relabelings to cancel things now. So until here, maybe you guys should agree. Because when I start doing relabeling, I'll change a lot of things. Okay. So remember that I have to take this formula exchange the mu nu, subtract, right? So if you exchange the mu nu on this one, you'll get this. But then you have to subtract this from this quantity. So this will cancel from there. Similarly, the exchange of this will cancel that. Okay. Yeah. And another thing you can directly see is that the mu nu exchange is antisymmetric here, right? Because commutators are antisymmetric. So you've already gotten one of the symmetries of the Riemann test. The other symmetries we'll see. Okay. Relabeling. Let us relabel. So this should be R rho sigma mu nu rho sigma mu nu v sigma. So let me relabel all the alphas to sigmas. Okay. In this equation, I'll take all the alphas, put sigmas. No, in this equation, I want to change all the betas, sigmas. Sigma, sigma, sigma. So now I can directly identify the Riemann. The Riemann rho sigma is equal to del mu gamma rho mu sigma minus del mu gamma rho mu sigma plus gamma. You should check this expression. If there's a mistake, you guys should do it again. I won't do this again. That's the Riemann. Yeah. Yeah.
You only need some gamma,
Huh.
which need not be the definition that we
Yes. Yes.
gamma,
Yeah.
and it's antisymmetric.
Doesn't even have to be symmetric. That's a non-metric gamma.
Yeah. So if it's non-symmetric, so then that term is
Sorry, non-torsion, not free gamma. Yeah, sorry, not non-metric gamma.
torsion-free gamma. So then that term is
Okay, I haven't done this derivation for torsion-full non-metric gammas. The rest of you can ignore what I'm saying for the next minute. So if you do put non-metricity, which is to say that the covariant derivative of the metric is not zero, and then you find a gamma such that that is true, okay, that's a very general gamma. It's not a metric gamma. And then you also don't put torsion-free condition. So then you don't have symmetry on the gammas. So you get a very general gamma. And then from that general gamma, you can find an R, of course, by just doing this.
So my question is that getting the covariant so we call that Riemann test, or the expression we still remain the same and we have just a torsion term.
Good question. I've never worked this out, so no comments. Yeah, I guess so. I mean, I don't know. I mean, when do you ever come across a torsion? You in a torsionful thing, you define the Riemann tensor with the form. I see, not the vector. Okay, but here it happens to be the same because covariant. Okay. Okay, this was something I had to explain because he asked, but okay, you want me to go into okay, you want me to explain torsion. Torsion is the idea that remember that this covariant derivative, this gamma, the Christoffel gamma that you wrote down, okay, we just got an expression and then we did things with that Christoffel gamma. But then if you're doing general relativity from a point, if you're doing Riemannian geometry from a more general point of view, you say, I want a derivative that transforms like this, okay? So then gamma just has that boxed equation per constraint, you remember? It has this tensorial part plus this extra part. So you say, I will just take a gamma that satisfies that. That gamma needn't be the G times del G gammas that Ashoke wrote down, okay? You can have more general things. And in that more general thing, you can have gammas which are not symmetric in these down two indices. And that anti-symmetric part is called the torsion. That's what the torsion is. But you will not see it in GR. GR does not have torsion. You don't have to worry about. Where does it have torsion? If you do like quantum corrections to GR, you can get torsion generally. They're connections. So a particular example of these full connections is the Levi-Civita connection, which is the metric connection, which has metrics in it. But you can define it for manifolds without metric even. But I don't want to go into all this. This is not for, yeah. You should probably ask these questions outside. Yeah. So that's the Riemann. Now you can find symmetry properties. Let's do it. Okay, this is something I just did not work out in my notebook, so you guys have to help me doing this. Symmetries of the Riemann. I thought we were, because I might. Is it on Zoom? If it's not on Zoom and if somebody wanted to attend, I should have received an email so I can check if you guys are concerned. I mean, I feel like it's being recorded on Zoom, so yeah, I haven't received any email, so should be okay. Okay, so symmetries of the Riemann tensor. One symmetry is already obvious, which is just, so I can bring this in. So now that we have shown that this is a tensor, I can do all kinds of things with it. I can bring it down, make it go up, make everything up, everything down, sum up, sum down, everything I can do. Okay. So then I can bring it down and say mu is equal to this is obvious because remember that I defined the Riemann with the covariant commutation. And the commutation is antisymmetric, so this is true. Yeah, for those of you familiar with Lie algebras, all these three symmetry properties should make a lot of sense as properties of the commutator. So this is from antisymmetry of commutator. Okay, the others I'd have to just check. There are probably very smart ways of seeing the other ones too. The third one, the antisymmetry in the last three indices, that has a very interesting meaning. It has to do with the Jacobi identity. But the second one should be easy to check, I think, which is just R sigma rho union equal to minus R rho sigma. Do you see a way of checking this? Okay, I guess we'd have to write everything down and do it. You want me to do this? Yes. Oh. You tried this. Okay, I haven't done this yet, so I'm doing this for the first time. So let's see. Yeah, okay. Right. Yeah. So you want me to show the symmetry first? Maybe you can show the symmetry first. Let's see. But yeah. Either which way, I need something that's all four down. So let me write the expression that's all four down. You were going to say something? Huh? Because it doesn't make sense to do symmetry operate. It doesn't make sense to switch indices up and down. Because remember that, yeah, I mean, maybe you can do it. I don't know. I just find it weird when such an equation is written up. I've never seen something like this. Maybe I'm wrong. Yeah. But I mean, but maybe there's a reformulation of this where one index is up. Doesn't matter. I'll just bring everything down, and this is where it's easier to remember if that's what you're asking. So if you want to remember the symmetry properties of the Riemann, antisymmetric in first two indices, when you bring everything down or bring everything up, let's do everything down. It's antisymmetric in the first two indices, antisymmetric in the second two indices, which are those two conditions, and it's antisymmetric. So let me write all the conditions. And it's antisymmetric. And it's symmetric under this, where you take the first two block, put it on the second two block, put it on the first two. That's another symmetry of the Riemann. And the final symmetry of the Riemann is that rho sigma mu plus 2 r rho mu sigma plus r rho mu sigma mu equals 0. And this is usually referred to as, I mean, just for you to look this up if you are looking this up, this is called the first Bianchi. I mean, people have names for all these things, but this is what's called the first Bianchi. And if you remember, there is an identity with the Riemann tensor with derivatives also, which I'll do next time. That's called the second Bianchi. That's what Ashoke has been calling Bianchi. Both of these are standard terminology. So if you ever see first and second Bianchi, it's just simple. You already know it. Okay, so these are all the symmetry properties. Now you want me to check this. I'll do this on the other board. Okay, first of all, let's bring everything down. So R, let me call it something else for the moment, just to avoid confusion. Alpha sigma mu is just, what do I have to do? I have to put a G alpha rho. I have to just multiply this equation with the G alpha rho metric. So it's G alpha rho. Oh, another thing that you have to remember is just, you can't just bring this down by bringing these down. Does not make sense. This is the disclaimer I gave you some time ago. You just don't take things and bring it down naively. This is not a tensor. Is this what you did? No? Okay. Del mu gamma rho mu sigma minus G alpha rho. Yes? You want to define this? Go ahead and define it. By what I'm doing right now. Multiply the metric. Yeah. Oh, sorry. Okay, fine. Epsilon this. Yeah, usually when you run out of indices, when I run out of indices, I just use xi because nobody uses xi. But people start complaining when I use xi, so I won't use xi. Okay, now we have to show a symmetry property. Let's do sigma epsilon mu nu. Right, that is the second property I'm trying to show. I don't know if this work, but let's just try. It's stopping sometime. Yeah, I don't immediately see how this will work. So, okay, let me try proving the third one first. So which is what? R mu nu. Huh? You want to write another covariant derivative? Don't think so. No. Okay, you try your best. Whenever you have expressions like these, you try your absolute best to do it with, like, at some level. At the Christopher level, you try your absolute best. If you give up there, then you go to that very dirty level of writing everything down. Okay, if I wrote all the gammas and g's, all the g's down here, this is, yeah, you probably can do it on a piece of paper, but not on a board. Okay, let me try doing this. So here, what do I have to do? What all do I have to switch? So this is a G mu rho del mu. Oh boy. You see why I didn't want to do this on the board? Rho mu is you guys should like tell me the symbols as I'm writing it. What? What? Yeah. I'm trying. Epsilon is a mu, rho del nu is a sigma, gamma, rho mu is a epsilon, sigma is a nu, plus g, epsilon is a mu. Yes, you have to do this once in a lifetime. Rho gamma rho mu is an epsilon. Sigma is a mu. Boy. Minus, yeah, I think it's becoming clear. Minus g. Epsilon is a mu. Rho gamma alpha. Nu is a sigma alpha. Mu is a epsilon. Sigma is a nu. Is it okay? Yeah, question is how do I show that this is equal to that? Yeah, I mean, I think the idea here is to just do integration. I mean, like, write this as a del of something, some full thing, and then just subtract. Yeah, okay, I see what will happen, but this will take me some time. It will take me quite some time. We'll do this next time, tomorrow. Yeah. So okay, so I will show the second, third, and fourth. The fourth, actually maybe you guys should try the fourth, right? Because I gave you a definition of the Riemann tensor. So why don't you try the following? So this I will complete next time. So we'll complete. But I want you to try this. The first Bianchi is just a consequence of Jacobi. And the second Bianchi is a consequence of something else, which we'll come to next time. So first Bianchi is implied by Jacobi. By this statement. You take a del mu, and then you take a del nu, and then you do a del alpha. You circle it around. Plus. Yeah, on a vector, say on some. I see it the other way around. I demand this and see that. Yeah. What gives you the Jacobi? Remember what gives you the Jacobi in an algebra? Everybody else just like close your ears for a moment. No, the Jacobi is a consequence of associativity of the algebra product. And the claim is that the algebra product here is associative. Okay, so associativity gives Jacobi, Jacobi gives Bianchi, plus Bianchi. Okay. So try this. I'm just giving you a very quick, easy thing. Okay, maybe it's not too quick because I did 2 covariant derivatives, I took some time, but you have to do 3 covariant derivatives, put everything together, you get an identity. That's the first Bianchi. Okay, let's stop here. Thanks for coming.